I'll offer justification for that. Well, going back to that equation there, I know that v squared is equal to 2g mass of x over r sub x. If I'm solving for r sub x would be 2g mass of that central body divided by this maximum speed squared. This is the formula for the Schwarzschild radius. Probably better pronounced Schwarzschild, but if any of you have a better German accent, then we'll stick with my pronunciation. And as mentioned before, he got caught in a mustard gas attack in World War I, and while he was recuperating, he came up with two major papers in general relativity, but ultimately died from the wounds, or from, in essence, his guns getting burned. So this would be the radius if the Earth took the entire mass of the Earth, shrunk it down. What would be the radius so that it would be impossible for anything to escape? So 2 times 6.67 times 10 to the negative 11th times a mass of 5.98 times 10 to the 24th divided by 3 times 10 to the 8th squared. I assume you had the zeros in there? Yeah. Units? Yep. It's a radius. So, double that, and you have a diameter. So basically, if the Earth could somehow keep its entire mass and shrink down to a space of roughly that, to a diameter of that, it would be a black hole. Let's do our sun. What is the radius of our sun that would create a black hole? The only thing we need to know that's different is the mass of the Earth, mass of the sun, and for that I will look it up instead of going off of memory. So mass of the sun, 1.99 times 10 to the 31st kilograms. Oop, 10 to the 30th, not 31st. So if the radius was basically a little under 3 kilometers, what's that, Peters Creek to Haynes Mall Boulevard? Is that about 3 kilometers? Ish. I think so. So if the sun shrank down to that sort of radius, it would be a black hole. Now what are the chances our sun will become a black hole? Pretty much 0. Stars have basically 2 processes going on. You have fusion going on, hydrogen binds together with hydrogen, which creates helium and energy. So we have this radiation coming out of the sun from all the fusion reactions. But there's also this gravitational pull of the masses. So we got this pull inwards. And the size of the sun pretty much stays the same as long as these are in balance, are close enough. As the hydrogen is used up, then we'll start, it makes it sound like it, oh, hydrogen's done, let's do helium. It's doing helium all along, but when the hydrogen runs out, helium's going to be the best bet. So two heliums smashed together to create whatever it creates, whatever, is it beryllium, lithium, whatever number 4 in the period. Oh, there's one right here. Beryllium. Or hydrogen and helium smashed together and create a lithium. But there's less energy coming out the higher, basically the greater mass you start with, there's less radiation coming out. And so if the star is massive enough, as the radiation starts to drop off, the gravitational pull becomes strong enough and it will basically collapse. If it is even bigger, I think I've got my scale right, it will collapse so quickly that it basically fuses again and then it will explode and then you get the nova and supernova. But if it collapses, then you, to a small enough size, you get a black hole. Now, as the energy is used up by a star, it also loses mass. So our sun is slowly losing mass, it's also losing energy and so forth. So what's expected for our sun is that the gravitational pull will become less than the radiation pressure. Go with the spirit of it. And our sun should start expanding. So, sun, Earth. So Earth is going around feeling fat, dumb, and happy. As the sun starts to expand, it's expanding because the gravitational pull is less, it's not holding itself together, and as it expands, the Earth will start moving to a farther out orbit. So eventually the sun will be here, where we are right now, but by then the Earth will be farther out, and humans long gone, unless we've spread out among the stars. So occasionally I hear people talking about the Earth will eventually be burned up by the sun. No, it'll be drifting out as the sun loses mass. So we have a smaller sun. It will not collapse into itself and create a black hole or a nova or supernova or any of the cool stuff. Questions to there or to here?
Earlier when you had the starting energy and then the ending energy, when all the final energy was going to zero, where's that energy going? The kinetic energy is going down, and also the potential.
The potential is going up. Don't forget the negative. Potential energy is negative.
Oh.
And also, the way it was presented is that I launch the thing, it has a total energy of 0 to start with. It's going to have 0 the entire time because after it's launched, the only force acting on it is conservative force. Don't forget, there was that plus C. If you needed to have some energy initially, just to ease your mind, you can make C whatever you want it to be.
Okay, that makes sense.
I guess properly what we did was the change in kinetic energy was equal to the negative change in potential energy. That in essence is what we were dealing with. Is that good enough?
Yeah.
Okay. Other questions? Let's take a break. We'll come back. We'll talk momentum.